Very good morning to everybody. So we continue our discussions regarding chapter 5. Okay, for the last time we already discussed about the few terms that you already will find after this. The first one is enantiomers, the isomers, how to determine the enantiomers or the isomers. Okay, and lastly, how you want to determine, you can determine the stereogenic centers, what is the mirrors, and lastly, you know how to draw the RNS configuration. This is very important things, okay, for RNS configurations. So we already also discussed, I give you a few question tests, okay, a question exercise. So we will discuss tomorrow afternoon, hopefully, okay. So for today, we'll continue regarding these meso compounds. As we know, compound C is the previous slide. It's compound C and D is identical, and we can conclude that this compound contain the plane of symmetry. Contain the plane of symmetry. So this compound is a meso compound, and it's a alkyl compound that contains tetrahedral stereogenic centers. Okay, so and the meso compound generally contain a plane of symmetry. This is the keywords. Okay, if we have plane of symmetry, we can conclude that this side compound and this side compound is similar, including the orientations. Okay. So because of stereoisomer of 2,3-dibromobutene is the superimposibles. So on its mirror image, okay. So there are only 3 stereoisomers, not 4. So first, what you have to do, by using 2 power of n. So in this case, they have 2 stereogenic centers. They have 4. You have to draw 4 stereoisomers. And lastly, you have to determine the correlations between among the stereoisomers. Okay, this is the easiest way. Okay, so and we already come in conclusions between A and B is the enantiomers because they have a difference in terms of orientation of the chiral centers. Okay, this is the chiral centers. Okay, and the correlations between A, B to C is the isomers. Okay, so in our training set questions, there is a few examples regarding this one. So it's okay if you want to text me personally. Yes, a few students text me, ask me to check the questions, but it's better for us to discuss among the others during the class. Okay. So RNS assignments for compound with 2 or more stereogenic centers when the compound have more than 1 stereogenic centers. Okay, centers. RNS configurations must be assigned to each of them. In this case, we know this carbon is S. Okay, you have to use the formula clockwise, anti-clockwise, and you have to make sure the priority number 1 should be in the front, and the priority number 4 should be at the back. 2 and 3 is on the plane. Okay, if not, you have to rotate and make sure it's in good arrangements. Okay, that's why if the compound asks you to draw RNS configurations, my advice is put number 2 and number 3 on the plane. Okay, number 1 and number 4 either on the front or on the back. Okay. So, okay, in this case, this is RS configurations, and this one is the R configurations by using this previous formula that we already discussed. Okay, so identical compound have the same RS designation, is very tetrahedral, stereogenic center, and enantiomer have exactly opposite RNS designations. Okay, so just change the positions between bromine and also hydrogens. You can draw another enantiomer of compounds. Okay, it's as easy as that. Okay, so the isomer have the same RNS designations for at least 1 of stereogenic center. and opposite of the last one of another stereogenic center. This is the real definitions of enantiomers and diastromers. But we will do more exercise after this to make sure you don't memorize the definitions. Okay, we have a few examples after this. Okay, so for cis-1,3-dibromocyclopentane stereoisomers, since they have two stereogenic centers, okay, here, all right, this one, if you doesn't want to make any confusions, just put hydrogens here, so you can easily find it whether this one is a stereogenic center or not. Okay, they have two stereogenic centers, so 2 power of n is become 4, and you have to draw all 4 stereoisomers. So disubstituted cycloalkane can have two substitutions, okay, substituents on the same side of the ring, which one is cis and then the one opposite side is trans. It's referred as A for the cis one and the B for the trans. The correlations between A and B is diastromers. Okay, this compound stereoisomers, but not a mirror image. Okay. For the cis-1,3-dibromocyclopentane structures, to find another two stereoisomers, if there exists, draw the mirror image of each compound. Again, this is mirror. Okay. So draw the second structures. Okay. So and determine whether the compound and its mirror image are superimposables. Can be superimposed. Okay. And cis isomer are superimposables. Okay, cis superimposables, and its mirror image making compound. This is identical. So A cis isomer is identical to this compound. Okay. So A is achiral mesocompounds. Okay, achiral mesocompound. So just do the mirror image, and after that you can find it. Okay. So if we talk about the trans, we already discussed about the cis, and now we move to the trans isomers. It's not in, okay, trans is not superimposables, okay, or mirror image. Okay, label C, making B and C are different compounds. Okay, and B and C are enantiomers. Okay. So because one stereoisomers of 1,3-dicyclopentane is superimposable on its mirror image, there are only 3 stereoisomers, not 4. Okay. Again, first you have to determine how many stereoisomers by using 2 power of n, and after that draw all the stereoisomers and determine the correlations among the stereoisomers. If they have 3, it could be more, but normally we just give 2. The maximum, otherwise you will miss out. Okay, the summary types of isomer. Isomer is a different compound with the same molecular formula. Okay, begins. It's chapter 1. You have to understand also the difference between resonance structures and also isomers. In isomers, they have 2 types in this case. One's constitutional isomers or isomer kedudukan, which is having atom bonded to different atoms. Okay, and for stereoisomer is related with the 3D orientations. Okay, and enantiomer, and we already discussed about the enantiomer and diastromers. Okay, and determining the relationships between molecules. Okay, this is kind of flow chart that you have to follow. If you find 2 non-identical compounds, you have to answer this question: do they have the same molecular formula? If they are no, they are not isomers. Okay. If they have, probably they have isomers, but you have to move to another questions. Are the molecule name the same except for the prefix such as cis, trans, ROS? So if there are no, it could be constitutional isomers. If they are yes, yeah, they are stereoisomers. But you have to answer the next questions also. Are the molecules mirror image of each others? If they're yes, they are enantiomer. If they are no, they are diastromers. Okay, it's kind of summary that we have covered for this chapter 5. Okay, optically active. The chemicals and physical properties of two enantiomers. Okay, we have R and S product, for examples, identical except their interaction with chiral substance. Okay, interactions. Okay, chemical and physical properties. Generally, this is a general statements. Okay, so they have identical physical properties except for how they interact with plane polarized light. Okay. So this plane polarized light is a light that have electrovectors of oscillates in the single plane. So the polarized light arise from the passing ordinary light through the polarizers, and the polarimeter is an instrument. Okay, we have the polarimeters. Okay. It's an instrument that allows polarized light to travel through the sample tubes contain organic compounds and permit the measurements of degree to which an organic compound rotates polarized light. So we know that the compound is RS configuration, for example, but we have to measure how many degrees they have been rotated. Okay, this is kind of instruments. The simple one, but it helps a lot. Okay. So with chiral compounds, the light that exists in the sample tube remain unchanged, okay, because for the chiral that doesn't polarize the light, okay. So for the compound does not change, the polarized light stays optically inactive. Okay. So with the chiral compound, yes, okay, it doesn't have any effect for the when the samples go through polarizers and go to the sample tubes, okay, doesn't give any angles for the lights. So for the with the chiral compound, this is different. Chiral compound, the compound that contain R or S configurations, the plane of polarized light is through the alpha angles. Okay, the alpha angles is calculated from here. This is the alpha angles. Okay. So the alpha angle is measured in degrees, okay, and called observed rotations. And a compound that rotates polarized light said to be optically active. It means it gives a response for the polarized light. Okay. So optically active summary, the rotation of polarized light can be clockwise or counterclockwise or anti-clockwise. So if the rotation is clockwise, we call dextro. Okay. Clockwise, we call dextro. It's positive values. If you remember that sugar, for example, they have D-glucose and glucose. This is kind of definitions of regarding the optically active. Okay. Anybody who are working on biologies, you are playing around with this, molecular biologies, for examples. In rotation is counterclockwise. Okay, the compound we call levo. Okay. It's a Latin words, so they have minus here. Okay. So two enantiomer rotate polarized light can be equal extent but in opposite directions. Okay, for examples, if enantiomer A rotates polarized light plus 55 degrees, the same concentration of enantiomer B we rotate minus 55 degrees. Okay, and if we combine between enantiomer A and enantiomer B, it becomes 0. That's why we call another term we call racemic mixture. So, okay, no relation exists between R and S prefix and the plus and minus designation that indicate optical rotations. Okay. What is the racemic mixture? Equal amounts of two enantiomers called racemic mixture or racemates. And the racemic mixture is optically inactive because the same situation here. If we put A and B together, A will be rotated 5 degrees, okay, clockwise, and B we rotate anti-clockwise 5 degrees, and it's become 0. That's why we call a wrestling mixture. Okay, this is just explanations about the wrestling mixture. Okay, this is the physical properties of enantiomer B, A, and B compared. Melting point identical to B alone, okay, and for the B identical to A. This is kind of tables, okay. Boiling points is vice versa. For optical rotation is equal to magnitude, okay, but opposite sign for the B. It's equal for the B also, and for the rest mix, it's 0 degrees, because again, if this one is 5 degrees, this one is plus degrees, this one is minus 5 degrees, it's become 0. So if they have a mixture between A and B, okay, the melting point and boiling point will be different. Specific rotations, okay, is a standardized physical constant for amount that Kira compound rotate polarized light. So you have to remember these questions. Okay, this question is very important. Okay, so specific rotation is denoted by a symbol alpha and defined using a specific sample length in decimeter. Be careful. Okay, not centimeters, decimeter. And concentrations in gram per ml. So if the concentration at milligram per ml, you have to convert. Okay, all about units. Okay, and temperature is a general temperature is 25 degrees, and the wavelength is we are using is 589 nanometers. Okay, you have to know that 1 decimeter is 10 centimeter. Okay, ingat balik Okay, form berapa I dah lupa dah. So optical purity, okay, enantiomer excess we call EE. Okay, is a measure of the how much the enantiomer is present in excess of the racemic mixture. It can be using this symbol EE. Okay, enantiomer excess EE is a percentage of one enantiomer minus percentage of another enantiomers, and you will get the percentage of EE. This one also you have to remember this formula. Okay, if you remember for the test set that I given to you last time, so okay, they have 3 questions regarding these calculations. So you have to understand and try to make it before we discuss tomorrow. Okay, consider the following sample. If the mixture contains 75% of one enantiomers, okay, and 25% of another enantiomers, okay, for example, we take enantiomer A, and this one enantiomer B. So the percentage of EE is 75% minus 35%. So, okay, it's become 50% EE. Okay. Oh, it's already there. Okay. So enantiomer excess can also be there's another formula. There's another formula, so you have to memorize. Okay, the calculated if the specific ratio of mixture, and the specific rotations alpha of pure enantiomer are known. So you can use this formula. Okay, for example, okay. So this is for the formulas. I think they have 3 formulas that you have to memorize. This one, okay. So for the physical properties of stereoisomers, okay. Stereoisomers, okay. Since enantiomer have identical physical properties, they cannot be separated by common physical technique like distillations. Cannot separate by common physical technique like distillation. Okay, so for example, because it's different. Okay, So the isomer and constitutional isomer have different physical properties, therefore they can be separated by, okay, the isomers and constitutional isomers can have different physical properties and therefore they can be separated by common techniques, for example, distillations. Okay, chemical properties. Wait. Chemical properties of enantiomers. Two enantiomers have exactly the same chemical properties except for the reaction with chiral and non-chiral reaction agents. Okay, many drugs. Okay, many drugs are chirals and often must react with the chiral receptors. Okay, that's why. And chiral enzymes to be specific. That's why anybody who are doing biomolecular, like myself, so they need to assign correctly the chiral center here, for examples, to make sure they are in the good arrangements in receptors, because in our body it's represented as a 3Ds. So it will have to captures or react with the chiral receptor or enzymes, okay, and to work effectively. Okay, so for example, like ibuprofens, okay, anti-inflammatory agents, okay, its active component agent is Motrin and Advil, okay, it's another name of the drugs, okay. So this R-fluoroxetine is an active component in Prozac. Prozac is a antidepressants drugs, or yeah, normally they are using for the mental illness drugs. Okay, once you ambil Prozac ni, you mengantuk lah sebenarnya. They will reduce your brain activities. So chemical properties of enantiomers. Okay, for example, one enantiomers of a drug may effectively treat like a disease, while there's another its mirror image. Okay, may be ineffective or toxic. Okay, for example, the easiest example is naproxen. Okay, it's an anti-inflammatory agents, and this is the mirror S with S configurations. With this one S configurations. Okay, we put a mirror here. I don't know what's happened to this, and we draw another enantiomers. Okay, for this one, so it's become R configurations. Okay. And again, it's a liver to toxin. So anybody who are doing synthesis for the drugs for this pharmaceutical industry, so you have to make sure and confirm the configuration of the compounds. Okay. So for the enantiomer and the sense of the smells, research suggests that odor of particular molecule is determined by its shapes, then by the presence of particular functional groups. Okay, for example, the caraway seeds have a S caravones. Okay, meanwhile in spearmint leaf they have the R caravones. They will give the different smell about these two compounds. The difference is only R and S configurations. Okay, for this one. Okay, this is the chiral center, not this one. Okay, this one is the chiral center. To put here. Okay, for molecular shape and sense of smells, okay, this is kind of applications of RNS configurations, also stereochemistries. For cyclooctane and another molecule have a shape of bind to particular receptors in the nerve cells that lie to the top of nasal passage. So bind result of the nerve impulse that travels to the brain, and we interpret the impulse from particular receptor as specific. Okay, this is what happened in our nose. Okay. Okay, I think that's all for the chapter 5, I guess. Okay, so we will touch a little bit about the chapter They have some recorded lectures by Dr. Yam because Dr. Yam insists me to show this slide, so I will do it. So this is about Fischer projections. This is another topics regarding stereochemistry, and it's usually used in biochemistry, especially in sugar chemistry. Okay. So for more detail, you can refer chapter 26 in your books regarding carbohydrates. Okay. And we just touched a little bit about Fischer projections. They have a few examples there in this subchapter. So you can do it and you can discuss with me. Okay. Fischer projections is as the stereogenic center in sugar are often depicted following the different conventions that is usually seen for other stereogenic centers. Okay. Instead of drawing tetrahedrons with two bonds on the plane, one in the front, one at the back, okay, the tetrahedron is tipped to the horizontal bonds, come forwards, okay, which is draw on wedges, and the vertical bond to go behind as a dashed line. These structures are abbreviated as a cross formula called Fischer projections, like a fishbone. That's why we call Fischer projections, okay. So the rules of Fischer projections, okay, a carbon's is the, I cannot counting, so I will change to the screens, okay. So the rules of Fischer projections, the carbon atom is located at the intersection of two lines of the cross, okay. The horizontal bonds come forward on wedges. Okay, the vertical bond going back on the dash. Okay, and in carbohydrates, the aldehyde and ketone carbonyl put on the near of the top. Also, in this case, okay, so we have this kind of aldehydes. Okay, so for the red color, we are doing at the wedges. Okay. For the carbonyl, usually we put on the top, and the horizontal bond we are doing, the vertical bond we are doing on a dash wedges. So it will represent like this. Oh my God. It will represent like this, and after that, just drawing a Fischer projections and mark as a R glyceraldehyde. Okay, and you should not rotate the Fischer projections formula in the plane of the page, since you are may inadvertently convert compound into its enantiomers. Okay, so the number of possible stereoisomers of the monosaccharide increase exponentially with the number of stereogenic centers present. For example, an aldohexose, okay, has 4 stereogenic centers. So it has 2 power of 4, 2 power of n, 2 power of 4 is becomes 16 possible stereoisomers or 8 pair of enantiomers. I think we not touch until the highest one we have given to the students, maybe 2 or 3, if I'm not mistaken, long time ago. Okay. So this is the representation of aldohexose in vertical representation or Fischer representations. You have to understand that in aldehyde and ketone carbonyls, usually we put near the top. Okay, so usually we put on the top here. So Fischer projection with multiple stereogenic centers. Okay, Fischer projections formula are also used for compounds like aldohexose, okay, previous structures, okay, that contain several stereogenic center. In this case, the molecule is drawn with a vertical carbon skeletons, and the stereogenic center have stacked one above another. Okay, using these conventions, all horizontal bond project forwards on the wedges, and horizontal. This is the horizontal part. Okay, bond project forwards and on wedges, and we will represent like this. Okay. Naming D and L isomers. I think this one is not really important. The most important things is how you can assign. This is the most important things. Okay, how you can assign the RS configuration to Fischer projections. Okay, R and S designations can be assigned to any stereogenic center, draw as a Fischer projections. formula on the following manners. Okay, the first one, you have to assign the priorities, similar that we are doing the previous lectures, how to determine the RNS configurations. So you have to assign the priorities. There are 4 groups, okay, Stereocenter using the same rules in section 5.6. What is section 5.6? You have to refer your textbooks, okay? So when the lowest priority groups occupy the vertical bonds, that is it the projects behind the plane on the dash line, tracing a circle in the clockwise direction give you, tracing the circle of the clockwise direction give you R configurations, okay. Meanwhile, tracing the circle of anti-clockwise direction will give you S configuration, as similar like the section 5.6, okay. When the lowest priority group occupy in horizontal bonds, okay, that is it. Okay, the projects in front of the plane on the wedges reverse the answer obtained in step 2 to designated of the configurations. Okay, this is kind of examples. Okay, redraw the Fischer projection using for wedges and dash and Stereocenter and label the center R and S. First, for the solutions here, okay, convert the Fischer projections, okay, formula representing the wedges and dash wedges, okay. From here, you can draw like this, okay, wedges and dash wedges, okay. So they have wedges on the horizontals, okay. And lastly, assign the priorities, okay. We have number 1 here, bromines, followed by CH2, because CH2 have been, because carbon have been connected with another oxygens, so it's become priority number 2. CH3 is become number 3, and also number 4 is at the back, okay. So from this one, 1, 2, and 3 is become clockwise circles, and 4 is oriented at behind. It's a configurations, okay. For the B, okay, we have to convert these Fischer projections to the dash wedges and wedges, and again you have to assign their priorities, okay. Chlorine will be number 1, okay. So compared to the aldehydes and also CH3, okay, aldehyde will be number 2 because they have carbonyls. Carbon will attach to 2 oxygens here, and meanwhile carbon here will attach another 3 protons, okay. And again this one is priority number 4, okay. So clockwise circle and group 4 oriented forwards, okay, its was is S configurations, okay. Lagi okay. So I think that's what we have finished today. So setengah jam. So you want to discuss the question today or tomorrow?
Tomorrow.
Tomorrow. Okay, we will do it tomorrow. So panjangnya ya, tomorrow. Okay. We will do it tomorrow. Okay. So I think usually for the Fischer projections, we just the type of questions that we ask you usually, okay, we already give you Fischer projections, okay. Draw the enantiomer, determine the stereogenic centers, draw the enantiomers and the isomers, okay, and assign the RNS configuration. That is it. Normally we ask during the final, okay. Don't nervous, okay. So I think we can finish by today. Please harvest what we have studied today, and hopefully we can discuss tomorrow for the questions, okay. Change 20 minutes, not 50 minutes. You want to discuss today? Okay, we will do 1 question only. I have to open my PowerPoint. It's okay for me. Tomorrow is okay. Today is okay also. Oh no, no, blank presentations. Okay, the first question is you have to label stereogenic centers, whether there is R or S configuration. So it's just question from the textbook. It's better. Okay, bon. So we have these A compounds. Okay, we have one stereogenic centers, and after that you have to go to the definition what we call. Okay, so it's you have number one here. Okay, so and after that you have number two. We start with the simples one first. Okay, and this one is number three. This one number four. So you have to put number four at the back. So in this case, it's already arranged for you. Okay, so it's become counterclockwise. Why? So it's become 1, 2, 3. Okay, it's become like this. Is nice configuration. So if you want to answer this kind of questions, okay, so it's become just label like this is as configurations. Okay, because if they have two stereogenic centers, and if you do S and R, I'm not sure where is S, where is R. Okay, it's better. Okay, so how to okay. So for the second one, I don't know what's happened to my pen now, so it's not response. Okay, for the B we have the questions. Okay, we have one stereogenic centers because it's already connected with different substitutions. So this one, to make it easy for you, label SSH3 here. So this one number one because it's nitrogens. Okay, this one is number two because it's carbon. Okay, and this one is number three. So this one is number four. Is clockwise. Okay, it's a clockwise. But you have to remember this one should be on the back. Okay, you will get R configurations, but you have to change to S. Okay, is the rules state there. Okay, so for the for the next one, okay, we have a one. Okay, this one is a CH3. Again, you have to make sure this one is the at the back. This one should be the S configuration. Okay, kita pergi laju sikit lah kan? So yang ni ada tunjuk, yang ni cari sendirilah. Yang C ni you cari sendiri macam mana kita boleh jadi S. Okay, fair and square lah. Okay. So for the last one, we discuss until these questions only. Okay, so for the last one, we have these two stereogenic centers. Okay, again, okay, you have to going back to the definition. What is the stereogenic centers? Again, to make sure everybody don't confuse, just put CH3. Okay. Okay. So again, this one, okay, this carbon is R, and this carbon is R. Okay. You buatlah sendiri. Counterclockwise kan, anti-clockwise you buat sendiri. And make sure both the lowest numbers, okay, the lowest numbers, this one, 4 numbers here at the back. Kalau dia kat depan, jawapan you tukar. Okay, like this. R jadi S, S jadi R. Okay. Okay. Fokus kan? Lagi. Okay, next. Label is stereogenic center as R and S. Okay, 5.15 in your books. Okay, just make a notes. Okay, like this is R. Okay, like this is S. So, okay, for this one, okay, find the stereogenic center. So in this case, this is the stereogenic center. Okay, fine. And label the purity. Okay, this is number 1. And this one is number 2. This one is number 3. This one is number 4. Make sure number 4 at back. Okay. And in this case, this is the S configurations. Okay, it's become like this. Okay. So for these two fellas, okay, for this one is R, for this one is S. Okay. Siapa yang dah buat tu dia tahulah jawapan macam ni dapat. Yang tak buat yang nak tunggu jawapan tu, memang macam ni lah jadinya. Okay. Okay, next for the C. Okay, we have two stereogenic centers. This one and this one. Okay, this one is not stereogenic center. Why? Anybody can answer? Why this one is not stereogenic center?
Group.
Yeah, they have two CH3. Yes, Lucas. Thanks. Okay. So, okay, again, okay, assign the priorities. Okay. So this one is R. This one is R. Okay. Okay, siapa yang buat dia tahulah jawapan betul tak? So for the last one, okay, we have chlorine, bromine, proton, and CH3. Okay, so chlorine, bromine number 1, chlorine number 2, CH3 number 3, proton number 4. Okay, this one is okay. It's good if you have a models, because sometimes you have to rotate, right? You have to rotate the structures 120, 180, something like that. It will easy for you if you have the models. Okay, so anybody who want to borrow the model from me, just come to my office. Okay. Okay. I think we discussed until now. Okay. I hope everybody are satisfied. Jangan gaduh. Okay. So I see in the chat box. Don't be like that. Okay, I think that's all for today. Thank you very much. I think we can stop now. So the most important things you have to understand for today, you have to memorize you have to know how to determine how many the stereoisomers in the compounds by using the formula is 2 power of n, and after that draw the all stereoisomers, and after that determine the correlations among the stereoisomers. Okay, whether there is mesocompound, identicals, and so on. Okay, diastromers or enantiomers. Okay, the next we already covered about the optically active compounds. What is the level? What is the destro compounds? And you have to memorize 3 formulas. In the end of this exercise questions, I already give you around 3 questions to discuss, which is we will discuss tomorrow. And lastly, we already touched about the Fischer projections. I think for better explanations, it's better to refer the recorded lectures, because one of our lectures have been made there. Because I'm not sure why we have to teach you Fischer, because it's chapter 26. Because we already said to you is cover chapter until 1 and until 11s only. Okay, I think that's all for today. Thank you very much. Hopefully to see everybody again next Thursday, I guess, around 2 o'clock. And stay safe, stay healthy, and we will see you again. Okay, bye bye.
Yes, come on, shorty, let's go. Girl, I see you over there in the corner of the dance floor, and I know you're acting shy, looking at the corner of your eyes. So I pick my heart up off the floor, move my feet closer to yours, catch my breath, and I say, I'm the one you're looking for. So come on, dance a little dance. Take my hand, darling, take a chance. You be my queen, I'll be your king. Show you everything that you've been missing, shorty. So come on, dance a little dance. Got me in a trance in just one glance. So don't wait no more, I'm more. I'm the one you're looking for, shorty. Girl, I see you over there hesitating, deliberating. You keep me waiting on a sign, looking at the corner of your eyes. So I pick my feet up off the floor, move my hips closer to yours, catch my breath, and I say, I'm the one you're looking for. So come on, dance a little dance. Take my hand, darling, take a chance. You be my queen, I'll be your king. Show you everything that you've been missing, shorty. So come on, dance a little dance. Got me in a trance in just one glance. So don't wait no more, I'm more. I'm the one you're looking for, shorty. I'll be the one you're looking for, shorty. So come on the dance floor and baby show me all your moves, all your grooves. Shorty, I got something to prove to you. So come on, take a little chance. Got me in a trance in just one glance. So don't wait no more, I'm more. I'm the one you're looking for, shorty. So come on, dance a little dance, dance a little dance. Come on, dance a little dance. So come on, dance a little dance. Take my hand, darling, take a chance. You be my queen, I'll be your king. Show you everything that you've been missing, shorty. So come on, dance a little dance. Got me in a trance in just one glance. So don't wait no more.